We shall define the Riemann integral in this module. The approach we take is due to Darboux, which is polished and refined version of Riemann's original construction. Without further ado, let's first set things up. So throughout f from closed interval ab to r is a bounded function. It's a bounded function. Our objective is to assign a meaning to this IAB of f, or in more common notation, integral AB of f. This is supposed to be area under the graph. Under the graph, the signed area to be precise. The signed area under the graph. Now we are going to take our approach motivated by the final axiom in the axioms of area that I listed. That is, a figure can be assigned an area if it can be exhausted both from the inside and from the outside by figures that are just adjacent rectangles. Now we are going to take this approach, so I need to make some definitions. Definition. This is the definition of a partition. So a partition P of closed interval AB is just a finite subset such that A comma B are elements of P. So it's just a partition P of is just a finite subset P of AB. It's just a subset of AB that also happens to contain the points both A as well as B. Typically, we list out the points of AB in this way. We list out A0 first, and then we list out A first and call it X0, and it's usually listed this way. And the final element Xn is going to be B. Okay, so we usually list the elements of a partition in increasing order, and this will make the notation of what is to come really transparent and straightforward. Okay, now for each subinterval x k minus 1 xk we define the lower sum with respect to, just a moment, first I need to tell you before, for each subinterval we define small mi to be infimum of f of x as x runs through. So let me use precise notation. It's just infimum f of x such that x coming from xk minus 1 xk, and capital Mi is just the supremum of f of x as x runs through xk minus 1 xk. Okay, so these should actually be small mk and capital Mk, because k is the variable that I have used as the running index. So on each subinterval you look at the supremum and the infimum of the values of the function f and call it small mk and capital Mk. Now we define the Darboux upper sum of f with respect to this partition P as UFP is by definition just the sum as you run over all the subintervals of Mk times the length of the interval. mk times xk minus xk minus 1. This xk minus xk minus 1 quantity, which is the length of the subinterval, will occur so frequently that we will just abbreviate it as delta xk. Okay. Similarly, the Darboux lower sum of f with respect to p is L of fp is by definition just summation k equals 1 to n small mk times xk minus xk minus 1. Okay, so these are the Darboux upper sums and the Darboux lower sums. Okay, what are we trying to capture with these sums? Well, let's just take a positive function so that things become easy when I draw areas. What we have done is this AB we have broken up into smaller intervals. So here is x1, x2, x3, x4, and let's say the final one x5 is B. Of course x0 is A. Now what you are doing is in each one of these intervals you are noting down which is the minimum point and which is the maximum point. So for instance, this point will be, this value is m0 and somewhere here this is m1. This is capital M0, sorry, this is capital M0. Okay, so what you do is you draw two rectangles, one with the one of the sides being of length small m0, the other side is of course of length, I should go all the way, the other side is of length of course x1 minus x0, which is just x1 minus a, and then for the second you use this maximum point, the length of the maximum thing, that is capital M0, so you draw this second rectangle. Okay, so similarly you do for all the other subintervals also. For instance, this subintervals, this is sort of the minimum, okay, and the maximum is sort of this. I hope the picture is not too confusing. So essentially what this gives us is this figure that comprise adjacent rectangles. You will get two pairs, you will get a pair of figures, one comprising the maximum points and the other corresponding to the minimum points. And it is intuitively clear that this adjacent rectangles formed by taking the maximums will sort of contain the graph, the area under the graph of the function f, whereas those corresponding to the minimums will sort of be contained within the graph, within the area under the graph, the region under the graph. Okay, so this is sort of mimicking the idea in the final axiom of the definition of area. Okay, now we immediately have this very simple proposition. Let P comma Q be partitions of AB, partitions of the closed interval AB. Then this L of Fp is less than or equal to U of Fq. No matter what partitions you take, the lower sum with any partition will always be less than or equal to the upper sum with any other partition. It doesn't really matter. Proof. Now, this should be obvious to you. L of Fp is always less than or equal to U of Fp. That simply follows straight from the definitions. At each subinterval you are choosing the minimum values for L of Fp, whereas you are choosing the maximum values for U of Fp. So this inequality that L of Fp is less than or equal to U of Fp is obvious. Okay. Now what we will do is both P and Q are partitions and therefore finite sets. Okay, first what we will show is if P1 contains P2, P1 comma P2 are partitions, P1 and P2 are partitions, then U of F P1 is greater than or equal to U of F P2, and similarly L of F P1 is less than or equal to L of F P2. Okay, so such a thing, this P2 is also called a refinement, of P1 for obvious reasons. The terminology here is very intuitive and visual. If one partition contains another partition, we say that the larger partition is a refinement of the smaller partition. Now what this is saying is, when you refine a partition, the upper sum has to decrease, whereas the lower sum has to increase. Why is this the case? Well, let us just see. As I remarked, all these partitions are finite sets. Let us consider a partition P1 and its refinement P1 union Z. I'm just going to add a single point Z to a partition, and let us see what happens in this case. This is a simpler scenario. So again, let's draw the picture. We'll draw a sort of sketchy picture where not much of the situation is fully captured. So you have x1, x2, x5, let's say, x3, x4. Let's say in the middle of this you are adding this point Z. Okay, so we have this functions which is somewhere floating in the air. What is happening is, when you compute L of F P1 union Z, okay, we have to compare this with L of Fp. Okay, now this L of Fp is just going to be summation k equals 1 to n small mk delta xk. This was our notation. Now what we will do is, we will just focus on this particular subinterval where all the action is happening. Everywhere else nothing interesting is happening. Well, I can always rewrite. So this is, in our notation, this is going to be delta x2, right? In our notation, this is delta x2, right? So what is going to happen? Well, you have m1 delta x1 plus m2 delta x2 plus so on. I'm not worried about the other terms, and finally you have mn delta xn. This m2 delta x2 I can rewrite as m2 into z minus x1 plus m2 into x2 minus z, right? I'm just rewriting delta x2 as z minus x1 plus x2 minus z. That's all I have done. Now if you consider, so this is L of Fp. Now if you consider L of Fp union Z, observe that all terms will be the same. Except these two terms. These two terms will possibly get lesser. Why will it possibly get lesser? Well, it will possibly get lesser because you are taking the infimum on a smaller interval. So when you take infimum on a smaller interval, it was only going to increase. Okay, so here you will have m1 delta x1 plus some m2 prime z minus x1 plus here some, let's say, m2 double prime x2 minus z plus m3 delta x3 plus mn delta xn, right? And we have m2 prime is less than or equal to m2 double prime is also less than or equal to m2. Okay, so this I have just sort of taken this point z to be in one of the intervals for concreteness. Specifically, we have taken it in the second one, x2 x1 x2 interval, but it could have arisen anywhere. It could have been anywhere and the same argument would work. So essentially what we have shown is L of Fp is less than or equal to L of Fp union Z. Okay. Similarly, u of fp will be greater than or equal to u of f comma p union z. Exact analogous argument will hold. Why you get u of fp greater than or equal to is simply because when you take the maximum on a smaller interval, it can only decrease. Okay, not the maximum, the supremum. When you take the supremum on a smaller interval, it can only decrease. So we have these two inequalities. So we have essentially proved this particular claim that when you consider a refinement, the upper sums will have to decrease and the lower sums will have to increase. We have just proved it for one point, but if P1 is subset of P2, P2 can be obtained by successively adding single points, right? You keep adding one point at a time. By induction, it follows that L of f P1 is going to be greater than or equal to L of f, fp1 will be less than or equal to L of fp2, and u of fp1 will be greater than or equal to u of fp2. Induction an easy argument through induction finishes this proof that the lower sums will have to increase and the upper sums will have to decrease when you do a refinement. Now, we might have been derailed from our original track. Our original track was to prove that LFP is less than or equal to UFQ. Well, that's easy. From what we have shown now. Consider P union Q. So this is a common refinement. Of both P and Q, right? So this is a partition that contains both P as well as Q. So it's sort of a common refinement of both P and Q. So how does this help us? Well, we know that L of F P union Q will be greater than or equal to L of Fp, right? And this L of Fp union Q will be greater than or equal to, will be less than or equal to U of F P union Q. Okay, and this will be less than or equal to UFQ. So this chain shows that L of Fp is less than or equal to U of Fq, which is what we wanted to prove, right? So essentially this argument was, we know the behavior of each one of these sums LFP and UFQ when you refine a partition, but the refinement allows us to compare LFPs and LFP union Q and UFP union Q and UFQ. Combining all these inequalities together, we get a proof. Okay, so what this suggests is, as you keep adding more and more points, let's go back to the original picture. As you keep adding more and more points, what is intuitively happening is that these regions that are enclosed within the area under the graph, these small rectangles that we have used, they will become larger and larger, whereas the rectangles on the outside will become smaller and smaller, right? So this is sort of mimicking what was there in the final axiom of the axiomatic characterization of area. So you expect that when you add more and more points, these approximations get better and better. So now the next definition should not be a shocker at all. Definition. We define the upper integral u of f to be just infimum of UFP as P runs through all partitions of AB. And similarly, L of f is supremum of LFP as P runs through all partitions of AB. Okay. Now, when do you say the function f is integrable? Well, let's highlight it as another definition. The definition of the Riemann integral. Riemann integral. If UF is equal to LF is a finite value, we say that f is integrable and denote this common value by integral a to b f. Okay. Now let me end this module with just a remark. You will sometimes encounter the notation integral a to b f of x dx. Now this is a notation that I neither fully understand what the motivation was, nor do I see how it adds clarity to the situation. You are introducing a variable x and you're putting a dx. Presumably what was trying to be captured is analogy with some f of x delta x, and you're just sort of shrinking delta x to 0, so you want to represent that infinitesimal quantity by dx. Now I guess this was the original motivation, but to actually make sense of this precisely, why you can write this as integral a to b f of x dx requires quite a lot of machinery, the modern tools called differential forms, to make this precise. So I will try to avoid this notation of writing the integral as integral a to b f of x dx. Okay, according to me it really doesn't add any clarity. However, this notation is prevalent throughout the literature, and as with many things, you cannot change centuries old convention. My favorite example is that of the electron. Why would you call the charge of the electron negative? The correct convention should be that the electron should be positively charged. After all of electricity is just movement of electrons, not of some positively charged quantities. It's of negatively charged quantities now in our current unfortunate convention. We can't go back in time and make the charge of electron positive. We have to live with it. Similarly, we cannot avoid this notation of integral a to b f of x dx. Many times writing it like this might help in computation when you are thinking about it very intuitively and informally. But it sort of misleads us when you are doing things formally and rigorously. Okay, so this concludes the definition of the Riemann integral. In the next few modules, let us see how do we determine whether a function is Riemann integrable, whether the Riemann integrable satisfies those two properties that we had listed as a characterization of the integral. If it doesn't, then this whole exercise would have been futile. So we will see all that in the coming modules. This is a course on real analysis, and you have just watched the